Okay. Hello, everybody. Hope all of you are fine and doing well. So, as you know, today we are going to talk about the neural network and deep learning. So far, we've studied different techniques of reinforcement learning algorithms, and we've covered almost the most important basics and the most important levels of the algorithms that are necessary to understand the higher level or complex techniques. So by knowing those algorithms well and those concepts well, even if you yourself go study the most advanced algorithm, you're going to see the just combination and mixture of different techniques and the different ways of update of the parameters. The only important change that we are missing so far is the bringing neural network and deep learning techniques into the game. After that, you will see that we just need to merge the value function approximation with finding weights techniques so that we can get rid of the table that we've had in tabular techniques, then have deep reinforcement learning techniques. Of course, there are many different algorithms there. We will try to, as much as we have time, also introduce them to make them clear for you. But of course, you need to study yourself too. For the neural network and deep learning, I know some of you guys have had classes. I know some of you have no idea what it is, and I know some of you are maybe good. So we have a little bit unbalanced situation, but mostly as I interacted and talked to students, they don't know, or even if they know, they don't know practical way and just know very in details and don't know what is the general flow. Of course, this is like full semester course that can be explained in detail, but today I'm going to explain it in practical and straight way and the things that we directly needed in deep reinforcement learning. So I'm not going to explain everything that is in neural network or everything that is in deep learning. I'm going to explain the topics and the details that we are going to use in reinforcement learning, deep reinforcement learning algorithms that we have, the most important elements. So, and for your project, of course, after this week, you can also choose deep reinforcement learning by just applying the value function approximation of the key learning on that soon we will also cover. But before starting, is there any question or comment or anything to talk about? Or any question about your project and you don't know how to choose or whatever you have problem, you can feel free to ask. Okay. Let's start then today's course. We are going to talk about first artificial neural network, then I will introduce the deep learning techniques and we will see what is it. First of all, the topic that we have, we will talk about linear classification. What does it mean generally? We will talk about the cost functions. We will talk about the optimization. We will talk about the backpropagation algorithms and neural network in general, and finally we end up today's course with deep learning techniques and what are the important parts over there. Of course, if you are interested in to study more and know more, you should have a look at neural network pattern recognition by Bishop, and another one is the supervised learning in feed-forward artificial neural network by Russell. That is a very famous book that highly recommended to study to know what is happening. Before diving in, why we have to, again, talk about neural network and deep learning, because we are not able to move forward in reinforcement learning algorithms unless we know what is happening here. There is no way. We must understand neural network and deep learning to be able to bring more advanced techniques and make our reinforcement learning technique more advanced and kind of powerful to solve bigger state space problems. So if you have a look at deep learning, where the deep learning is standing, we can say we have the artificial intelligence that I discussed a little bit at the first class, that what is it and what kind of techniques that we have. In 1950 it started, and it was engineering of making intelligent machines and programmings. Then about 1980s, after that, the machine learning started, that like we wanted to, without explicitly programming, if else is everything, we have some algorithms that can do it for us. So we didn't want to write, okay, if else for loop, if else for loop for everything. We wanted to have some functions, some codes that can make decisions based on the input and output. Those kind of algorithms are called machine learning. That it was like 1980 to, of course, it's continuing. It started in 1980. Then deep learning basically is recently become more popular, and 2006 to 2010s. Then learning-based deep learning algorithms appeared. So if we want to have another look, what is it looking like? We have artificial intelligence in bigger scale. Inside AI, we have machine learning algorithms, that is subclass of AI. And inside machine learning techniques, we have deep learning techniques. So it is sub kind of field of the machine learning techniques that we want to see. So we say, although the neural networks date back to decades, and it's very long time that we are working with neural network, but why deep learning recently became more popular? There are multiple reasons. One reason is the big data. Recently, we have access to big data because with deep learning, we need to have access, access to lots of data. And recently, we have larger data sets because of internet resources mostly, and we have easier collection and storage of data. For example, like 10 years, 20 years ago, if you had like millions of pictures, hundreds of thousands of pictures, you should have hard disks. And that was very hard to have it. And you didn't have fast internet to have it on, online in cloud, for example. But nowadays we have it. So that like ImageNet is one of the famous ones that we can get lots of data from there. On the other hand, second reason why deep learning became more popular is the graphical, the GPUs, or graphics processing units, that nowadays, as you know, like if you are playing games, of course you know, we have very strong graphic cards. And if you know about like machine learning and deep learning techniques, we have GPUs with CUDA cores that CUDA cores are enabling us in order to do faster processes. So what does it mean? Why GPU is faster than CPU? Because with GPU we have multiple cores that they can do repetitive processing. So with CPU we have maybe one core that can do multiple tasks, but GPU 100 or 1,000 of cores can do one process that is similar but 100, 1,000 times faster. And this makes it very suitable for image processing and big state spaces. So we have like image, each one of the pixels can be calculated by one core of GPU, so that whole process can be run in one step. Please. So if you want to do this process with CPU, then your CPU, even if that's 8 cores, so you need to do like 8 by 8 to process the image. This takes longer. But when you have GPU to do calculation, all of the frame maybe can go to the GPU and in one step come output. Because of that, we have hundreds of times faster speed. But basically, GPUs are not able to do, like, these 8 cores can do different processes, but this GPU basically can do like process of sum or multiplication all together in one stage. But anyway, based on this reason, we have hardware that enables us to use deep learning, bigger giving whole image as input, for example. And nowadays, very recently, we have very advanced graphic cards that NVIDIA H100 Tensor Core is new graphic card that is introduced like last year. And this also has some capabilities that not only GPU is inside, it has CPU inside too in order to handle the data. And it has also a processor for connecting to the network directly, so that you don't have bottleneck of your data comes to motherboard, goes to your own CPU, calculated, and come to GPU. Instead, NVIDIA introduced very new graphic card that everything is inside, and it can process directly lots of data much faster. And it's claimed that I think 144 times is faster than normal existing graphic cards, and that's very exciting to know, because after we finish like advanced algorithms, you're gonna see that it's still having faster GPUs can be very useful to learn all details of environment in so that our agent can try every possibilities to learn better. On the other hand, we have lots of softwares that enables us to use deep learning techniques, like first of all, new models and techniques that we will see some of them, they are new, and new toolboxes most importantly. Why new toolboxes? Because if you want to implement everything yourself, it is brutal, very hard. You need to write all the details of neural network and everything in detail, and if you want to try 20 different models yourself to see what's happening, then that takes a long time and you cannot have progress at the end. But we have with new toolbox like TensorFlow, PyTorch, Keras, and Kuden, and different libraries, we are able to quickly do and finalize the project that we want. So these are reasons that makes us easier to do the job. Before starting to talk about neural network and deep learning, there are a couple of concepts that I will try to explain to you. First of all, we need to know a little bit about linear regression and what does the prediction means. I already briefly explained to you, but let's say you have this plot and you have a bunch of data. So this is for advertising on TV data. It means that you have a product and you want to sell it. As an engineer, you produce something and you want to sell it. And you know that after, like for different products that you have, you know that after advertising on TV, the sale is increasing. And these are samples for different products and the sale. Now, the idea is with linear regression, we want to predict the line, predict this data, so that we can say, okay, if new data comes that I haven't seen, like if something new comes, I can say approximately, if I spend this amount of money, how much my sale will be increased. So I have hundreds of samples of different products, and I want to say, if I invest $1 million, 500K, how much will be my approximately sale? By looking at data, this data we can say by having a technique, for example, linear regression, finding this linear line, so that with the input that I'm giving, I can calculate the output. So here you can see a linear model. When we are talking a linear model, it means that we are finding a linear model that is a line, and its function can be written like this. F of x, that since we have had f hat of x is equal to some term. This term includes two parts, a bias, beta hat 0, added by the linear function. That one is indicating the slope of line, this part indication of the slope of line, how it should be, and the bias shows where it should be. So my purpose as developing different algorithms is to finding these two parameters, so that I can draw this line in linear regression. If new data comes, this blue comes, then the line can predict the data for me, that what should be approximately input. If it's here, it can approximate with some error. If it's here, we can approximate with some error. That we also discussed it. We call it root mean square or RMSE error. Is it clear? On the other hand, although this model is good, but reasonable, but it's not fitting very well. We can have like more flexible model that we can call it as quadratic model, so that this curve you can see fit our data much better, and this can do the prediction job much better. So as a developer, as machine learning algorithms, my purpose is to have better fit line for my data. Is it clear? Okay, now you should think, when we are talking about data and prediction, what is its relationship with reinforcement learning? Who can answer that? Wait, you wait a little bit. Others? You guys over there. Hello. You guys over there. Answer the question. You should listen. If you know, answer it. If you don't know, you must listen to the class carefully. Okay? So we have a bunch of data, and we are predicting with some curve. It means that we give input, we expect output. We want to say, okay, new data comes, where it should be. You can imagine these data are the experiences of our agent that we had. We said our agent is trying in the environment many times, right? We were calculating the experiences robots were trying in the environment. And they were based on the try, some value function as output. We were calculating a value or Q value with some terms. So the data can be different tries. The output can be different Q values or value functions that we have. So generally looks like this. We will see in detail, and I will explain how that's happening. So, any question? We say finding manual features are hard and time-consuming if we want to do this, because like if you want to find these values manually, of course we can do. But if you find it manually, or some codes that finds it, it's hard. That's one challenge. Even if we do, usually it's not scalable for all the other parameters and techniques that we have, and it's like instead possible to learn underlying features and parameters for our model. What does it mean? Later I'm going to explain this very well. We can say, this is an important topic. Instead of having calculation of all general data, we can kind of consider low-level features that we have. We can consider we can extract some low-level features from environment that we have. If we have image processing problem, like instead of if we want to detect the face of human, we can extract low-level features and mid-level features, and based on mid-level features, we can extract the face. For example, your agent is seeing the environment, and we're gonna detect the face. And if we're gonna detect the face has some features. Face has eyes, ears, nose, right? And of course, the computer doesn't have that. If I know those features, like in different levels, for example, chair has no eye, but human has it. And your agent is trying to interact with human, do something, action. So I can kind of, with deep learning, can see how low-level, mid-level features can help us to extract high-level features, so that these high-level features or mid-level or low-level can be fit into my reinforcement learning algorithm that I will gonna explain today in detail what's happening. So for now, we want to have general perspective. Another example is you can consider elephant. or different kinds of animals, the features that we can have in low level, mid level, high level. And for example, car, detecting a car, we can have these features. In order to be able to do that, of course, we talk about neural network first, then deep learning, then convolution, then you will see finally how we can merge all these to reinforcement learning. And another example is chair, for example, the lines that are including some parts, edges of the, for example, chair, the wheel, and finally this can be indicated as chair. So with that background of machine learning, artificial intelligence, and deep learning, let's first of all break it down and talk about artificial neurons. So they are known as also perceptron or node, and they call that simplest element of artificial neural network. And the idea comes from the inspired by biological neurons that is existing in human brain. So we have different elements, and these different elements is kind of motivated us to say, okay, if you have a neuron like this, that there are some input and there are some output, how we can bring it into computer system? How it can be possible? If we go to the next slide, we can start to talk about the similar perceptron, a neuron or perceptron, in form of forward propagation. So what does it mean? It means that we want to have a neuron, some inputs, some outputs generally, okay, in general concept. But how it looks like, formally we call it forward propagation, and it means that we have some inputs like x1, x2, x3, and xm as inputs, and one bias term. And what is this bias term? If I go back to the slides with linear regression to understand it clearly, I told you that the slope in linear one, simplest, slope of this line, and where it should be, up or high, down. The bias indicates where this should line to be, and this term over here says what is the slope. So this is linear. If I go to add more dimension, for example, quadratic, I have one more element, one more variable, but bias only one, where it should be. So when I'm talking about bias, it's not very complex. It just indicates where it should be by linear regression. So the same thing is happening in the neural network, and one perceptron also has some inputs and one bias. Okay. Number of inputs can vary, but yeah, let's move it to see. Each one of the inputs that I have, again, by referring to linear regression, you saw that we have some weights for that. We want to kind of find some weights for these inputs, adding some bias to fit our data, to find that line that fits my data. That's how it looks like, input, some weights, and finally I want to sum them up. Sum of the weighted elements. Then, after doing this sum, I need adding some nonlinearity that I will explain what does it mean and why we need to do that today in detail. So after summing, adding nonlinearity, then we have the output. So this perceptron says, based on these inputs, I want to find the output that gives me my desired, I want to find the weights that gives me my desired output. In machine learning, almost all the time, when you see y means output. And when we have y hat, it means that predicted output. Don't forget this. This is like golden rule. And x's usually are as input. And if I want to formally write the equation for that, I can say y hat, output, prediction, is equal to this term. This term has different elements. For example, h is adding nonlinearity So far you don't know what is it. I'm going to explain soon. We're going to get into it. Then we have bias where the prediction line should be added by sum of xi's, wi's, sum of weighted inputs. So what we are looking for to find are these w's, finding proper weights in order to predict our data with minimum error. So that my plot data, I want to find better line with finding w's for the equation that I have to minimize the error. But minimizing error, I will explain how. This nonlinearity, I will explain how. And the whole procedure, we will see soon. Is it clear so far? Any question? This is called a perceptron and or a neuron. So it should be clear for you that we can write the same equation in form of linear algebra and say this here bias added by the vector of x and w's, so that I have lots of x's as input and lots of, for each one of these x's I have weights and w's that we want to find the w's to train our network generally. All objective is to find w's. So now let's talk about the activation function, one of the missing elements. We want to add nonlinearities into the network by activation function. So based on that, we can say linear activation functions adding resulting in linear decisions. On the other hand, nonlinear activation functions usually gives us opportunity to approximate nonlinear functions. Something similar that I explained so far. So we can have linear and nonlinear functions in order to add it into my perceptron. So what does it mean? It means that we want to decide what is going to the next neuron. So we have the inputs, we have the weights, but the output that we should decide kind of what should go past to the next neuron. And there are some reasons to decide on it. You may say, okay, I have inputs, I find good weights, why should I decide to go what goes to the next neuron? The reason is that there are millions of parameters that we calculate in the weights, and the numbers and the weights that we are calculating can grow exponentially, right? Every time we summing up, and sum, the value is increasing. So we kind of need to control it. That's the reason that we have, one of the reasons that we have the activation function there, to kind of don't make it grow the number every time summing up the values. In neural network is not very crucial important, but in deep learning networks, because we have many layers that we will see, we need to prevent it. How we show it? Nonlinear activation function usually can be shown as G or H. Both our terms can be used here. So I represent it H, and we say that the activation function that we usually put here, all of them are nonlinear, because we want to kind of have better estimation and predicting nonlinear functions to have predictions. So what does it look like, this H? We have different approaches, different techniques to replace with this activation function. One of the famous ones is sigmoid. And as you can see, for sigmoid, we have like H of Z that is equal to one term here. This term represents this sigmoid function that is popular and suitable for probabilities, because the value is between 0 and 1. Whatever input you give, it brings it between 0 and 1. So it means that whatever comes out from the sigma that I have x's as input, weights, and whatever comes as output, I feed it here, and the value, whatever it is, comes between 0 and 1 based on this function. Kind of limiting it, like making it more compact in this form. This is sigmoid. On the other hand, we have hyperbolic or tangent h, another mathematical equation that is in this form, and does the same job, just limiting it. And also, we have very important activation function called ReLU. That with ReLU, we can just simply say h of z is equal to maximum of the 0 and z. It means that the outputs of neuron, if they are negative values, we don't care. We put 0 instead. For the parameters that coming as input of neural network, whatever I am doing, if the value is 0, less than 0, I plot it as 0. I replace it with 0. Otherwise, whatever the value is, I put it itself in linear form. So, but now you should see some problems over there. What do you think now is the problem over here? The number again is too big. We will see how to prevent it in next slides. Yeah. Because with sigmoid, you see that it's limiting there because it's like curve like this, curve like this. It's not exponentially growing, but here exponentially again growing. In order to prevent that, also we will see how to do it. So there are many, many different techniques in order to do this. There are many. These are the most important ones, and ReLU is very important for us for deep learning because there is vanishing problem, and when you do this, you are losing some data over here. But with ReLU, we don't lose it, and that's the reason that we have the ReLU as a common technique, but kind of we should see how we can prevent it. We have another approach called leaky ReLU, that in leaky ReLU, the idea is that don't throw out the negative values over here, and with some small slope do the same job, but practically the idea sounds nice. If you have negative value, kind of use it, don't throw it out, but practically it's not working very well. It's still ReLU is more common to use, and ReLU is working better in deep learning by experiences and tries on different models that already scientists did. So any question here? So we have input, we have weights, then we have activation function so far. An activation function kind of wants to limit the sigma. And one point that before I forget it, that the input that you're giving to your neural network should be normalized. If you have data of x, y position or something big values, you cannot give it to the network directly. You should normalize it usually between 0 and 1 or -1 and 1, then feed it to your network. And the output, if it's normalized, then the output is normalized too. If it's not classification, then you have probability or some value that you should consider the input was normalized between 0 and 1, the data that you've had. Also, this is practical note that before I miss it, I would like to mention it to you. So yes, I explained it in this slide that we have gradient vanishing problem, that using some activation function for each perceptron, we may lose some data every time, because here you can see that in sigmoid function we are losing some data here every time it decreases. But ReLU has not that problem, for example. Here I also indicated, especially with normalized data between 0 and 1, you can see that we are losing data over there, and it makes it shrink, shrink, shrink. And if you do this process too many times, then you see that your input and weight is like useless. The impact is already vanished. Solution is using activation function that has that problem, and this is the ReLU that I explained to you, and it's very common in deep learning. But there is a question that sometimes is important to ask. Is the ReLU linear or nonlinear? So some of you answer, please. ReLU is linear or nonlinear? Huh? What? Nonlinear. Who else? Your friend thinks it's nonlinear. What do you think?
Also nonlinear.
It's nonlinear. Why? Because so you have, if it's nonlinear, it should be a direct line, continue. But it's nonlinear, it's straight over here. Because sometimes they think that, okay, this is like linear, but it's not. It is still nonlinear. So as I mentioned, activation functions must be nonlinear in order to be able to model those. Is there any point? No. As I said, as I explained, the disadvantage of ReLU is that it's directly past the output of the greater than 0 to the input to the output. The solution is one of the solutions is batch normalization, and it means that if we want to normalize output of the previous layer. So whatever the output is of, if you have multiple neurons, we can normalize them again. We can again rescale them between 0 and 1. That's it, simply. So you have some inputs that is between 0 and 1, for example. Then you add some weights, then it increases. Then again do some normalization to again bring it between 0 and 1. That's one technique to deal with the problem of the ReLU. Of course, we are maintaining the distribution of data still, and it can be used in several points between different layers. At end of each layer you can put it, but also you can put it in some layers output, because you know that if it's increasing too much, then at some point you are decreasing it again. Now let's have a look at one example to make it more understandable what is happening. Very simple example. We say, okay, we have two inputs for our neuron, and let's see what is happening. If the bias is 1 and the W1 is 4 and W2 is -7, whatever, we have some random weights over there. And for given data, if the input is like 4 and -7, and since the bias is like 1, then what is happening? Then we can say the y hat predicted output is equal to this equation, the h of the b added by xt w, then we replace the values. So we can write h, 1, replace the 1 over there, x's, inputs, whatever they are, and the weights, 4 minus 7. Then by calculating this, simply we can write the y hat is equal to h of the 1 added by 4 times x1 minus 7 times x2. And it's a line in 2D, in two-dimensional space. So whatever input is now, I put it instead of here, and then I have output, of course, applying nonlinear function after applying nonlinear function. So here there is an example of 1 added by 4 times x1 minus 7 times x2, that you can see that this is the line. If you add this equation, you will achieve that line. And if, for example, we give the input as -4 and 6, some values for x, then you calculate it, you have some value. That this h of -25 is minus 1.38, and that comes from sigmoid. So if you give this -25 to sigmoid function, the output will be 1.38. I calculate it for you and demonstrate it over here. If whatever it is. If you have ReLU, what will happen? Because it's negative, it will be 0. So the activation function just will be calculated for you there. Another example, like if you have more data, 3 inputs, 1, 4, 5, -3, then the same term, a little bigger term. and we will have h of 1 added by 4x, 5x2, and minus 3,2, and it will be 3D line. I demonstrated in 3D shape for you, in 3D workspace, so that you will have a plane instead this time. So this hyperplane is kind of, it demonstrates this equation over there that gives me the output that I want. It means that this hyperplane, it means that in 3D space, if you give input by x, y, z, and this hyperplane kind of is split it into two. Based on the input that you have, will give like left side or right side of the hyperplane, if you want to understand it in 3D visually. If you have more dimension, 4 dimension, of course there is no way to demonstrate it for you guys anymore, then it will be calculated automatically. Of course we usually have more. So now we can formally write the output as if you want to add more perceptrons, we can write z is equal to bias added by some of the inputs, weighted inputs, so that based on that term we can have multiple outputs instead of one. So I can call, usually we call in neural network z with numbering z1, z2, that each one has like one output. This perceptron has output of the y, that is going to the again activation function. Then z1, z2 are my output. The equation then this time looks like this: z of I is equal to b of I, so that I can, per each layer I can different biases, and some of the weighted xj's, wji's this time. So that indicates the different nodes. I put it a note here that here we have dense layer. Dense layer means that all of the elements are connected, like input connected to other in this layer some z's. So if you have 5 nodes here and 2 here, then for some like x1 is connected to both, x2 is connected to both, and if I have 10, it's connected to 10. All are connected, we call it as dense. For implementation, we have different libraries and tools. PyTorch is one of the most famous ones, and Keras, TensorFlow are also nice to use. But we prefer to work with PyTorch in reinforcement learning because we have some simulations, like we have Isaac Gym that only supports PyTorch, for example. Due to that, we would like to work with PyTorch more probably, more likely. And also it is easier than the other ones, more close to Python programming language. Based on that, I also show some, put some codes here that, for example, if you want to create the perceptron, you can like import torch.neuralNetwork as NN, then you can create a layer, neural network layer simply. How you do that? You write layer 1, for example. You want to create this layer. Exactly this one that I demonstrate, I've written the code in Python. 2 line, you can create this perceptron. Layer 1 is equal to nn.linear. We want to create a linear perceptron with number of inputs, number of outputs, and if I want bias or not. So all the background calculation, these sigmas, weights, whatever I have already implemented, you don't need to re-implement anymore. We don't need it. If you want, you can, but we imported torch, neural network.linear, number of inputs here 3, 2 output, 1 bias, true. That's it. So during these slides, I usually put also the examples of the implementation, whatever needed, and finally we conclude that if we all put all together, what will be the output? So we say basically there is an unwritten rule that minimum one hidden layer neural network with enough number of nodes can solve almost any problem of prediction for my problem. So this is valid for neural network and known. Of course, we need proper amount of neurons, and we need proper activation functions in order to achieve it. Having more will be helpful, sometimes makes it easier to train, but one layer basically is enough for like prediction tasks and the things that we are doing. But you may say, why in deep learning we will have more layers? I will try to clarify it soon, that what's the reason. Because there we have also feature extraction problem, because we also want to extract the feature itself out from the data that we have. The feature is not ready for us. So, any questions so far? I'm trying to explain all the important elements. If you have any question, please ask. Some of you may find it a little bit complex, some of you may find very easy. So depending on how much you know, I don't know. Because of that, if you don't understand, ask what's that part, what is this one over there, so that later you don't have problem. So let's have a look at a typical training procedure of the neural network, how we can train our model. First of all, we define the neural network with some learnable weights, as we've seen in the previous slide. Then we feed the input through the network. We give the data that we have as input. Then we compute the loss. And the loss is comparing the output with ground truth that we have. What does it mean? It means that I want to buy a home, for example, or a house. So I have some data, and these data, of course, like you can consider price and size. Then these have some value, for example, 2, 3, and whatever it is. Okay, these are my data as input. What I want to do, I want to feed this data as input to my network, so that my neural network finds some weights that indicates a line over here. And after I give some new data, 5 and 6, it gives me output. For giving, So based on that, we have some error here, that this error should be indicated as loss function. These are true data that I have. I know the values and I know the output per each one, so that we want to compute the loss based on that and update our weights on the network. That I will explain how. In order to update the weights, we usually want to propagate the gradient back into the network. It means that I give the data, my data moves forward to the output. From input, I have the output. Now that output, I have some true value. I can compare it. After comparison, I have error. Then I can propagate the updating of the weight on the network, so backward. So usually the common way is forward, then backward. Backward is for update that we will discuss it soon, what kind of techniques we have and how we can do that. So the one step is here, propagate the gradient, update the weights of the network, and usually weights can be updated by W equal to differences of the W and the learning rate and gradient of the change that we have. How it can be achieved, this term, we will also discuss today. So again, we feed our input, we get output. At the beginning, it's something wrong, right? Because we don't know weights. Something random, initial random weights I have. I give my input, I get output. Something very stupid and wrong. But I want to kind of find a technique to adapt my weights every time. And by trying this many times, I want to adjust weights to find proper prediction line to minimize my error. If you want to have a look at the single layer neural network, how does it look like? We have input, bias and input, number of hidden layers. Again, we have bias here. We can have bias here, Z1, Z2, Z3, ZL1, for example. Then I have, for this case, I have two outputs, Y hat 1 and 2 as output, and couple of weights. Weight 1 indicates the weights over here, layer 1, and weights 2 indicates layer 2's weights. That we can write, for example, if we want to calculate these z's, first layer, I can write the same equation, zi bias 1, sum of the input and weights, x's and weights. Then, if I want to calculate the y hat, I need to consider these two layers. What I do, like the activation function, beta 2, the second bias, added by the sum of the h1z, activation function and z, first layer output activated, times the second layer weights over here, then I have the predicted output. This is almost whole mass of the neural network that is happening in lower level. But usually, we don't do manually. We just call the library and it does it for us. No need to calculate it ourselves. You can do for learning, but for solving real problems, we don't need it. So here I've demonstrated one example. Z1 is equal to, for example, B1 added by X1W1, X2W2, and XMWM that represents one of the lines of calculation for Z1, for example, over there. Z1 because comes from X1, X2, and XM. Sum of all of these goes to calculation of the Z1 added by bias. And if we want to see how that is happening in multi-layer, what we need to do simply, we can we can declare two layers continuously. The same code, import torch.neural network as NN to call it again. Layer 1, neural network.linear 3 and 4. For example, here 1, 2, 3 input, 1, 2, 3, 4 as hidden layer. I have activation function and second layer that I want to have 4 as input, y4 as input, because the output of first layer is 4. Input of the second layer should be 4, right? This is 4. Output of first layer, and this becomes input of second layer. This should be 4, the output 2. 4, 2. Simply. If they are not same, you will have error. Then calculation will be wrong. So when we call linear here, in Keras is different, in other tools it is different, but here when we write linear, it means that it is dense. It means that all the layers are connected to each other, simply. Now, what does the deep learning mean generally? Deep learning means that we want to have a lot of those layers, multiple hidden layers. So neural network becomes deep learning, just having multiple layers over there in middle, simply, not very complex thing for now as the basics of the neural network. So you can see different figures and demonstration and how we can do the calculation, the same, but we have multiple layers here. Z1, L1, L2, Lk, that I added one element here, that Zk minus 1, so that indicates Zk this time, different layers calculations with the equation that we have. And over there I also have shown that you can declare it like with some variables and linear m and h1, h1, h2, h2, hk, hk2. So the implementation of this deep learning, deep neural network that is linear is over there. A few lines of code you can do that and train your simple neural network if you want, that we will see how to train also. So we have another one simple example, success of swimming in competition. I already set you example of the buying home. Here you can say, okay, if you consider we have one element as number of hours that you're training for swimming practices as one feature x1, this is number of hours of practicing. Another two number of hours of dry land workouts you do practicing gym, running, whatever to make you stronger in order to participate in competition. We can consider that already we have some examples from some participants, how many hours they swam, how many hours they practice in dry land. Then based on that data, we can say, okay, how successful they were. We can say these guys that practice a lot, they are more successful. They get trophy 1, 2, 3 second places. These guys like didn't get any. So based on that, if I have new one, my neural network or my deep learning or network that I have, I want to predict it. So how that is happening, you can see that we have like some value over there. Then if I have this simple neural network with two x1 and x2 is as input, z1, z2, z3 in my hidden layer, y hat 1. For simplicity, I didn't normalize it here, but we usually normalize it. So if we directly feed the x1 as 32 and 21, the values over there, then it looks like this. 33 and 29 goes to the network, and finally the prediction comes some value. That if like if the data is here, this guy is successful, we're supposed to see, for example, 1 as output over there. And since at the beginning, without training, the value will be wrong, something totally wrong. But meanwhile, what we need to do, we need to calculate the objective function or cost function, how good the weights are, in order to be able to update it. To do that, we can write the objective function of my network. We can say error of the weights. This is indicating error of the weights. Sometimes we indicate it with J, and mostly or sometimes in different books and resources you may say J of W or E of W is equal to a function that indicates loss. In the left side we have prediction that this f function f says my neural network we've given x's as input and weights that I calculated. What is the output of that one? Differences of that with the label, with the true value that I know, for example, if this guy is successful or not. So based on true value and the differences between the prediction of my network, I have a value that indicates my loss, how good my network is. Right? Then what I need to do, I need to generalize it for calculating whole network loss by saying that, okay, the average of, for example, 1/9 of all the network weights, 1 to n, I want to calculate the differences of all of them, and I have one loss for my whole network, one value for my whole network. Based on that one, then I can, so one of the techniques also can be here it's just, so let me clarify this. Writing loss function has different ways. One is, so this is for one node. If I want to calculate for all nodes, this is average. And next slide is mean square error. So second technique of calculating loss. We can have different techniques of calculating loss in neural network. Why this one is not very common to use? Because we have average, and average we have, if we have negative values, then it becomes the negatives and positives goes away. Because of that, we would like to have an error that negative values does not affect, and we use mean square error more likely than average because of this square that is here, and find the differences of the, doesn't matter if it's negative or positive, just finds the differences and hold the differences of the prediction of my network and label that I have for my data, then the average of that becomes my whole network error. At the beginning, my network error is very bad, but I want to kind of improve this error. Finally, I have a network that predicted my true values. Any question? How you can do that? Simple 2 lines. Loss is equal to, oh, I've written 2 times, just one of them. Neural network.ms mean square error loss. So you indicate that your neural network, NN, wants to use mean square error loss. If you write NN dot, you can change it to other ones too. Then output equal to loss of the Y and prediction. This is the label, and this is the prediction of the output. Then you can calculate the loss and put it on, in the output. With one line, you can get it in PyTorch. So, for example, in this network, let's say we have these numerical values as input. X is 32, 29, whatever the values are. Then go to here, and the output is like this. So different outputs I have. So per different tries that I have. So one time I give these two, 39, 22 as x's. One time 28, 32 as x's. Then per that one, 90, 78, 55. I get it as output. And I know that my true values are least. For first element, I should have get 95. I'm getting 90. For second one, I should have get 80. I'm getting 78. Third value, 72 must be true, but I'm getting 55 as prediction, so that the differences between two can be calculated by mean square error, and that's my network error. Clear? Good. There is another techniques, as I mentioned, different techniques for calculating loss. Another one is binary cross entropy, that is used for when we have probabilities form and they should be between 0 and 1, so that we can use cross entropy error. It's usually used for classification problems. Not very good for our application, but if you're developing some codes to finally say that, okay, this is classification, the output is true or false, or the probability of you have lots of y's as output, and it choose probability of being like object X. You're feeding image as input of your network. Then you say, okay, probability of being cat or dog. Then output can be cat, dog, and all objects. Then probability of which number is higher then can be used as cross entropy. The equation is here, and it just does the output as log of the differences. Log of the differences, nothing very special. Average of log of the differences that finally gives you the probability in probabilistic form. You see that 0.2, 0.9, 0.5 instead of direct value, so that it can move to 0 and 1 as classification problem. How you can do that? Again, you can write loss equal to neural network.cross entropy loss. Then output is equal to loss of the Y and prediction. That's it. 2 line, then you can apply cross entropy. So, any question? As I mentioned, what we want to do, we want to minimize our loss. Actually, we want to update our weights of network by minimizing our loss. How we can do that, what does mathematically looking like, the objective that we have, is like weights that I want to find is like this term over here, that are minimum of the average of the loss function that I have. This is loss function, differences between the network output and real output, and I want to minimize it. That these W's are the weights of my network and can be represented in this form too. That W star is equal to arc minimum of the error of the weights. So based on that concept, we can say we have loss optimization, and we have optimization problem that want to optimize the loss. So this is the objective function. W is argmin of the error of the W's. Now you know how it is calculating. And if we visually want to demonstrate it, we can say that, so in this 3D plot, this is our solution space, so that what we want to do, we want to minimize our problem. So that at the beginning, based on the weights that we have, random weights that we have, we are somewhere over here. So for example, if you have two weights, W0, W1 over here, the error of W0 and W1 can be like indicated over here on one specific problem that looks like this. Then what we are going to do, basically what is the ideal way going to do is kind of finding the gradient of this point, and after finding the gradient of this point, moving toward minimization of that point. So of course, mathematically we can take a point and find the gradient of the point, and based on that gradient point we move toward minimizing that. So general idea is look like this. So if you continue this process, this concept of minimizing the loss, every time taking a step toward going to minimum, of course it leads us to some better solutions. So this is whole idea of loss optimization, but we have formal techniques in order to be able to do that. What they are looking like, one of them is gradient descent. Gradient descent says, okay, so we have different techniques in order to achieve this problem that I said to you. From somewhere to minimize our weights. Gradient descent says, okay, what to do? Algorithm. Initialize weights randomly on my network. W should be randomly something. Then loop until convergence. We have a loop up to convergence of the weights. Compute the gradient, and update the weight. So how we can update the weight? We can write W is equal to W subtracted by some learning rate and gradient. So this gradient added by some learning rate and decrease each time the weight, because it's minimization and updating the weight. If I have higher learning rate, it will be quickly go down the W, weight will be changed faster. If you have lower learning rate, the W will be changed slower. So for each one of the weights of network that I have, I want to compute the gradient and update it. So, but this has problem that next slides we're going to improve it. But how we can do that in PyTorch, you can see we can write optimization, or one variable as optimization is equal to torch.optimum.sgd. So this one is stochastic gradient descent. That next slide we're going to show. So model.parameters, I give it as input. Model.parameters, that includes all the parameters. The learning rate that I have, this eta here. Then the momentum of the change that I have. And finally, you write optimum.step. So this updates whole weights of W's of network that we have. So you give the input, goes to the output, then you want to update the weights with these two lines. The algorithm that you want, you can apply on your network. But of course, we need to also consider some points that we will discuss. So how that is mathematically looking, if we want to just not ignore it too much, just a little bit see what is happening. If you want to have a look at just one line of input to output, X to Y, so let's say we have a node, one node as input, one node in our hidden layers, and one node is in output. So the E of W can be calculated by this term over here. that the gradient of the error, this one, can be calculated by the first part, the weight of the gradient and the gradient of the output W and the weight 2, so output W and weight 2 times this one, the W1 and the Y1. So the gradient of this is Y hat, and this is the error based on this one. Then after calculating this stage and this stage, we need to come to this stage and add it to. So here, here, and here, third element, to find the gradient. So that is happening in that term over there. Just representing mathematically generally what is looking. What about the learning rate? One of other points that you should be careful to consider it is if you have a small learning rate, convergence will be slow. We want to minimize finding W's that, like, let's say best value for W is over here. So if my learning rate is small, then the step size will be small and it takes long time to come down. But you may say, okay, I can increase the learning rate. What will happen then? We should be careful. If we have large learning rate, in the other hand, then let's say the step is too big, and from here the learning is jumping there. From here, like jumping there. So you may never even achieve this part over here, because after come down, maybe it go up back again. The size is too big. Like you wanna go in the hole, but your step size is too big. Then you're never gonna end up in the end of hole. Your step is too big to go there. You need a small step size to go inside. So that is happening over there. That we should find proper learning rate, and this is one of the challenges that when you're training one neural network or deep learning, you should find proper learning rate there. But by experience, by looking at other codes, examples, implementations, you can put default good values over there. So that this learning rate usually for this size is working nice. So you try it, but of course it doesn't work, then you change it, finally it works, and that's it. There are automatic ways too, but yeah, later we don't have time to discuss those in details. You should study as researcher. So one of them, I'm going to explain it, one of them here, but there are much more sophisticated ways too. So let's see if we want to deal with this. One of the ways that we can do is trying different learning rates, as I mentioned. Other one is the adaptive learning rate approach that will help us to adapt it. How does it look like? We can say adaptive learning rate methods are kind of optimization of gradient descent methods, and the goal of minimization objective. The goal is minimization of the objective of adaptive learning rates, that they can be dynamic with based on the gradient size, momentum of the learning, and particular weights of the size, and etc. These are elements that can be effect on that we have. So based on that, we can say, okay, we can use SGD, we can use ADAM, we can use AdaGuard, and we can use, for example, RMS prop. That can be our basic optimization in order to optimize our loss function. So generally, what does it mean? It means that, so as we said, we want to find the minimum of the loss, that I have based on the W's. Then these different gradient descent techniques, these algorithms can help us to do that. For example, SGD, if you want to implement for your network, you write optimizer equal to torch.optimum.sgd, so that you give again your model and parameters. It means that the network, and you give the learning rate. And this was the learning rate that I was mentioning finding that is a little bit challenging. In one of these slides, I also explained what does it mean and how we can a little bit work with it. So SGD, Adam, if you want to use Adam, you just simply write torch.optimum.Adam. If you want to use AdaGuard, you use like .AdaGuard, and this is RMS prop. There are many more that depending on situation you can use them, but this like SGD and Adam are more common to be used. So you may say, what is the momentum? I mentioned it already. So you need to study more in detail to understand mathematically how does it look like, but it is a method useful for adjusting faster convergence. It kind of boosts the learning rate to converge faster mathematically. But yeah, I'm not going to explain exactly how, because that's the thing that you can study if you are interested. So let's have a look at the gradient descent first, then SGD next. So as we said, we initialize the weights randomly, then loop convergence, we compute the gradient, update the weight. But this SGD, this gradient descent technique computes the weights that is computationally expensive because it calculates the weights for all of the gradient for all of the points that I have. What does it mean? It means that so in order to predict and update the weights of my prediction, for each one of these data points, it updates, it finds a gradient. And per each one of them, finding the gradient, of course, is computationally expensive. That's called gradient descent technique. This is whole the scenario, whole the algorithm. So in order to solve this problem and improve it, we have the stochastic gradient descent technique that exactly is the same thing, but this time just picking one single data point in order to do that. We say the motivation is, so finding gradient of all and update the weights is not very like efficient. Instead, we can say, let me write with other color. This SGD, just we can say, okay, if I want to update the weights and the bias, or like most importantly the weights that I have, then like choose one, and based on the gradient calculation of this one, then update the prediction. For example, update it like this. But the problem is, it is stochastic. It means that randomly we choose one. Every time that we are improving the prediction, we are destroying the other side. You see? So randomly we choose from here, we try to adjust whole line, then whole line is like one time is improving, the other side is destroying the prediction. So of course the idea is do it many times to fix it, but if I do this, it's balancing and balancing, and that's not very efficient. And on the other hand, the better way to consider gradient of all in order to update my weight, that's better, but that's also computationally expensive. In order to deal with something better than this gradient descent and this stochastic gradient descent, in order to update my weights, there is a stochastic gradient descent with mini batches. I'm sure you've heard, if you're familiar with a little bit neural network, you've heard about mini batches that says instead of choosing one point, choose n number of points as batch of data, then calculate the gradient of those data, the average of gradient of all of them, then update the weights. It means that, so red, green, this time I do it with blue. It means that instead of one or all, just do for some randomly, then calculate based on these gradients, then update the weights based on those samples that those called as batches and mini batches. So the whole scenario is same, updating of the weights based on this calculation. Here we find the gradient of those batch points, then based on the learning rate times that one, I'm updating the weights. Very simple calculation. Weight updated by the gradient times the learning rate that I have. Okay, this is called SGD with mini batches. So whole concept is this. Implementation is one line if you want to use PyTorch. So what does it do? It updates weight for me, weight of the network. Clear? So also I shown already how to implement it. Like SGD is like this. Whole that algorithm can be written by optimizer, then torch.optimum SGD. You give the model, network model, that you define number of layers, how many hidden layer or input output, then comes as input, learning rate, then apply SGD. That's it, one line. And this, when you do when you run it, then it updates the weights of network for you. Now, if I'm looking at this graph here, we should say, let me start from this one, from left side. The blue lines are some data. And I want to predict some, have some prediction based on this data that I have. And this orange one is true function. So it means that the best ever function for prediction is this orange one. I know it already. My network I want to predict have some prediction of this data, that this line, the blue line over here, can be a prediction. But this prediction is not good at all, because like if I give some input as x here, or if I give the y as input here, then x is wrong. The error is too much. And here error is too much. In here error is too much. So when you have a model that does prediction but is not doing well, we call it as underfitting. Your model is underfitted. On the other hand, if your model, based on the data, is predicting well, we call it as ideal fit. On the other hand, you may have a model that exactly runs all the data, and you see this blue line follows most of the data that I have. So this is called overfitting also in neural network concept. And what does it mean? It means that my network, so the error is very good. You may say, okay, so the prediction is very nice. Whatever I give as new data will be very nice, right? But actually no, because this learned this data exactly, and it is not generalized for new data that maybe is here. So the prediction for trained data is good, for test data is very bad. When I'm using train and test, you may don't know what is it, so let me quickly explain it. I have to compact all the information in short time to pass to you. Hope you get it. So when you have like dozens of data of something, images or samples of data, let's say these are your data, what we do usually for trained neural network or deep learning, we don't train our model with all of these. If you train all your data with data set, all of these, then you don't have any data to test it. We usually like take 30% off, keep them as test data randomly. Then you train your model with these existing remaining data, then you have some output and you minimize your loss. Then to test it, This data that network never seen, you feed it to see how much is the accuracy. That makes sure that, okay, if new data comes that your network never seen, it will work well too. It's not only working with data samples that you have. Maybe you achieve 99% accuracy here, but that's useless because if new data comes, the error is like very big, totally wrong prediction. That is because we have overfitting here. To prevent it, we try to train our network with some data, and finally we report the test data error, not train data error, to say how accurate our model is. And there are also different techniques that usually we try to uniformly, randomly choose the data as test data, also not choose like some of them that is like very similar. So I had a student that I asked him to implement something with deep learning, and he cut a folder image of folder from somewhere that was like exactly similar, and he trained very high accuracy with other one, and he said I have test and train, but he cut it one folder, not sampled from all. And I was impossible, how come you have that high accuracy? And when I looked at the data and saw that he missed some part of, like the car data set is missing, the less accuracy is high. So that's the thing that you should be careful. Underfitting, idle fitting, overfitting concept, very important to know. So because we also need it in reinforcement learning, so we try to have idle fit. So how to solve underfitting problem? Underfitting problem means that my parameters are not good, learning rate is not good, the layers that I have are not good, number of nodes that I have is less than needs, or the technique. So you should adjust it to get idle fit. But how to overcome overfit? You want to remove your nodes or something? So solving this, we know that there is something wrong. We don't have enough learning rate, parameters, or whatever to achieve. But if overheat happens, then how to solve it? One of the technique is regularization that says, okay, we can improve the, so what is the regularization? I first define it, a technique to prevent overfitting, improve the generalization of the model for unseen data. And if we consider we have a network like this, what is happening? I am doing randomly I'm dropping out some of the nodes or activations as outputs of my network every time. So that it means that we calculate x's, we calculate the x's, and we calculate the weights of each one, but randomly, for example, 30% of them, every time I'm making them as 0, resetting them. Kind of forcing my network forget something, not memorize everything, so that this can prevent overfitting. This is called regularization of the network and dropout solution. So how to do it in PyTorch? Neural network, we write neural network that dropout. Probability 0.3, 30% every time automatically will drop out by my PyTorch algorithm. Okay, clear? Good. So here there is a visual, much more understandable way to how to understand also after doing that how to stop training process. We can say, okay, number of steps that you want to train your neural network also is important element, right? Although we do regularization, although we have well parameter adjustment, but how to know when to stop our training steps, how to know it. So we can say, okay, let's based on the iteration that I have, draw the loss. At the beginning, my loss is high, then the loss is decreasing. Here, I just show the test data loss and train data loss both together. So it means that I am using train data to train my network, but I'm testing it sometimes with test data. But I don't update the weights. I don't do back propagation. I just do forward propagation for this one. So I'm training my network by train data and plotting, and sometimes also I'm testing with test data to see how is the accuracy. So by plotting this up to here, we can see that this is underfitting up to here. But here, after that, we see that our test data, if I'm not wrong, yeah, our test data goes wrong, my train data goes better. So this is the point that better to stop my training, where divergence is happening. This is automatic way of training neural network when to stop it. How many iterations you should try to learn your neural network to make sure that everything is fine. Automatic way is like that. You split your data train test, you train it by train test, sometimes you test it by test. Then you see in some point they start to diverge, then you stop it. It is the best point to have general solution for the problem that you have. Any question? So another example here, more clear. This comes from regression book that is coming from machine learning. We usually discuss it in machine learning. So if you look at this one, we have a bunch of data. The black line is ground truth, the best model that we can have for that. So we know it already, the best model is that. The orange one is the underfit. The prediction line underfit is one model. On the other hand, we have the blue one. The colors is not very clear. Green one, that is overfit, that fitted the data well. And the blue one, that is good fit. If I show it with MSE for the flexibility of my model on the overfit and underfit, you can see this color, orange, blue, and green are representing different ones. So underfit is over here. It means that for also this one is test, the red one is test, and this one is train. You see at the beginning the model that I have, underfit is over here. If I train it more, the train and test coming down here, the blue one is here. And as soon as they start to diverge, if you start, the blue model is best one, but if you continue more, your neural network to train it, then for example, the green model is over here. That test data is going worse, but train data is getting better. The error is getting downer for train data, but for test data it goes bad. And that is the green one over here. But which one we prefer? We don't prefer the model that is trained very well for our training data. Although you may say, okay, my error is decreasing, that's very nice, my network is learning, but that's bad. You should stop it by testing your test data when it's diverging over here. This model, blue model, is the answer that we are looking, not this green one. Clear? This is a beautiful point that you need to implement for your neural network and deep learning to make sure that your training for all data is generalized to solve different problems. You're solving image processing problem, machine vision problem, then you say, okay, I recorded video. So some of the students of our lab also is solving some magic show. So my data is working very well for 100 videos or pictures that I've collected. It's very perfect. Then you go to competition or where you test, the guy comes, works, or it doesn't work. Oh, why this is not working? That's because of this. You didn't stop it in well. You may stop it here. Although your accuracy is 99.9, but this won't work for new data. You should have stopped it here to make sure that with like 90 instead of 99, it will work better. Okay, I think a little bit of rest, then we continue. Okay. pay attention to continue class. So far, what we've learned that we have artificial neural network with some perceptrons inside, we have some inputs as x, and we have some output as y hat. So that input can be anything, output can be anything that we want to predict. So far we've learned this. In simple network we don't have too many layers, hidden layers, but in deep network we have too many layers. And why we need to have too many layers when we have a lot of x as input. So this x as input can be directly image, and we can feed our image of something like some person is over here, and we want to detect it or do something, and finally do classification and say what it is. So far we've learned general concepts, and we've seen how the process is happening, and even we've seen simple codes of each independent parts. But now we want to a little bit open it and a little bit move toward deep learning and open deep learning much more, because if we want to use simple neural network and simple layers many, it is difficult to detect the image and what is happening. It's better to find out some features to train our data and make it more smarter that what deep learning is doing. Because of that, we are going to talk about that. So first of all, let's talk about the ImageNet. ImageNet is a large visual database designed for visual object recognition. It is, there are more than 14 million images that they are annotated by hand. It means that, so in neural network, as we mentioned, output, to calculate the loss, we need the output. And the output means that we need to have label of data and the output of data. For example, here in an image, it means that we have an image that includes different things. Labeled, somebody sits and label this and says, okay, the guy is over here. The person that I'm looking over here. There is a cat is over here. There is a car over here. These called labels of data on image. So in the ImageNet, we have 14 millions of images that's already, they are handmade, annotated. We know the labels. And when you are going to train some model, develop your algorithm, you can take the output as wise in order to be able to calculate the loss for yourself. So because of that, that's very famous data set. But apart from that, not only the labels, the bounding boxes also is important. The bounding boxes shows what I draw here, the position of start and end of each one. This is called bounding box. Usually we count the position of start of the box and end of the box. That this is used for localization of the object, not only detection. Detection classification says, okay, this is cat or dog. So the other image is human or what? So this is the classification. But we sometimes also not only say what is the, if this is the guy, what is the object inside, but also where it is in the frame and image that I have. That's also called localization. Meanwhile, we are finding the class of the object that we can indicate with bounding boxes, so that bounding box is also indicated for more than 1 million images over there. But apart from that, we have different kinds of networks of the deep learning that they have different architectures, different configuration of this network. That, like, if you look at this graph here, 2013 we started with the AlexNet introduced. Then we have different kinds of techniques like VGG19 in about 2019. And we move to much more advanced techniques. And you see the performance accuracy on ImageNet dataset that during the time they are increasing and doing better. AlexNet prediction was something like 65% accuracy. But now we have modern techniques like over here that you can see that model solves a SOPs that is 2020 VITG 14, it has very high accuracy. These small block points that you can see, there are different architecture of deep learning techniques. All of these are different techniques and architectures. That do you need to know them? not really. We don't need to know them. Just we need to know the ones that are in the higher edge, and these are doing better performance. You need to have a look at these techniques, which one is doing better on this data set. We may have a look at other data set, and this algorithm over here does very bad in another data set. Other algorithm that is in middle does better in that data set and that application. So anyway, these are different neural network architectures that are doing, has been used in different works. For example, if we specifically talk about image and visual information, first of all, let's answer why it is important for us as reinforcement learning developer, algorithm developer. Because we are preferring our robot looks at the environment, and with pure image that our agent sees from environment, decide what to do. Instead of giving specifically detecting that this is like this is whatever I want to do, this is the object that I want to pick. If I am developing an agent to pick the object, but not exactly saying what to do, my agent, by seeing the environment, can make decision. Because of that, because of this concept, we want to also talk about the higher level of what we can do. But let me also mention, all the concepts that I'm talking about, image and visual information, is not limited to pictures and images. It can be LiDAR scanner input, or it can be robot joints as input. We have lots of data that we can make it as data. Doesn't matter if it's picture or it is some sensor information from any kind of environment. If we go more in detail, you will understand what do I mean. So we say visual information can be represented as array of numbers. First of all, what does it mean? It means that you can say we have a picture of a bird. Of course, a picture includes 3 colors, RGB, that I can represent them separately. And each one of them, if I apply grayscaling and converting this red one to grayscale, and this one can represent different information for me. So that, for example, I can have a picture of 400 times 800, that this 400 times 800 size of image that I have, if it's RGB, will become times 3. Then 3 times of 400 times 800 I have with one frame. Then each one of the RGB colors, like this blue, can be between 0 and 255 for indicating how much blue is, how much green is, how much red is. So that for only one picture that I have, the input is 400 times 800 times 3 times 255, just one frame. And if I want to have deep learning or algorithm that technique that interprets this in ordinary way that we studied, all of that should be as input and go to lots of neurons and millions of maybe weights over there to calculate, to understand what is happening. Okay, so because of this, we would like to kind of prevent this and kind of improve it, to make it use some techniques to reduce the dimensionality in order to able to understand what's happening in this frame and what is this, for example, bird here. Another example here, 16 times 22 times 1 times 255 times 1, because we can say, okay, we don't need RGB to detect and do whatever I want. So in many applications, we don't need the colors. You can throw out the color. At the beginning, convert it to grayscale. Then you have one dimension. For example, reading number, handwritten digit. It doesn't matter if you're written with blue color, blue pen, or red pen. You just need to read the number. Then grayscale, you have one dimension. And each one of these, like pixels, representing some value between 0 and 255, that how much gray is, how much white is, and then represent some input for our problem. This is also a very famous problem, that hand region, that neural network does very well as input, then says, okay, the prediction for this characters is like 8, 2, 3, whatever it is. In computer vision tasks, I basically focused on regression problem. I already explained to you, but also as also we can mention, it can be classification problem. Regression is for prediction of my data that also we are focusing on to use in our application. But sometimes classification is important, that we want to just find a class of data. So for example, here it is cat, here it is human or bird or whatever, classify them, so that from regression even we can go to classification by adding cross entropy on the end of the network. They are also tightly coupled. The whole scenario is similar. So classification, regression tasks, localization tasks can be like localizing bounding boxes. Here you can see the just simple concepts of when we have pictures. Actually, we have array of data. This array of data can be included in form of probability or normalized value. Can be also, this goes to the input of the value that we have. Localization and bounding boxes, this is output of the one famous algorithm of YOLO that detects different objects, can be, or classification that you can see like different kinds of objects, birds, like different kinds of animals for doing classification visually. But what it is important for us, not only machine learning, not only deep learning, for our reinforcement learning course, is to extract high-level feature construction. Because if your robot is looking at environment, then each pixel is important for us. Our state space is too big. Instead, we rather to extract important features. For example, the chair, the human, important features, high-level important features. In order to do that, what to do, like here, high-level features of this image is like we have like lips, eyes, and if we can detect lips, eyes, like tongue there, then we can say this is human if it includes these parts. If we have like a motorcycle, we want to detect it. Of course, this motorcycle includes with like some elements that represents the motorcycle. If you have a car, like wheels, doors, the windows frame, and headlights, so can lead us to easier to detect this object that we want to find out in the image that we have. Can we do that manually? So, like, can we do this manually? So that determine what eyes look like or what vehicle looks like to detect it? Yeah, we can do. Before deep learning algorithms, we had many techniques in machine learning that could do this for us. But the problem was that with those techniques, we needed to know the knowledge of the each domain, exactly how we can define a chair, how we can define objects in image processing, but we have signal processing, we have many different applications in chemistry, in medical science. Then the algorithm that we were developing for NLP, that was like brutal with manual detection. So feature identification, so not only the knowledge, the feature identification is also hard. The classification of feature were also hard. Because of that, we needed to not only about that, also we need to like deal with the image scale, deformation viewpoint, the noise on the image, illumination, and many other problems. Like you can see that we have viewpoint, you have a tiger. You say, okay, you write if else some techniques that if there is an animal that has 4 legs, this can be like in this class. Then the animal rotates, then 4 legs are not on the floor. Then how your manual extracted features can detect this is like a tiger, lion, or whatever. Illumination, you can see that like the guy is like the color is like black. Then there is no noise, no eyes to write if else's to find if there are eyes, this is human. But we would like to generate, or deformation, you can see deformation example. So we would like to have more general techniques that still can say this is human, still can say this is animal, or still can say this is like a doll. or whatever it is. So that we want to prevent manual feature detection with introducing learning feature detections by first detecting low level, then detecting high level. How this can be possible detecting low level, we will see in what with introducing convolution. So the idea is to learn features in hierarchy form from low level to high level, and also we are not limited only for image. We are talking about image to make it more understandable. You're not limited to like only for we can use it in image. Anything, any problem we can use to detect small features in order to get the higher level features. So I already answered this, but the question is why feature extraction is important for reinforcement learning. Now you can say that the state space can be smaller then, because instead of interpreting each pixel in RGB times big values, then we can say interpreting just the monitor, just the table, just the person over there. If your robot is following line, just detecting the line by the features. If your robot is industrial arm using some objects, just extracting and detecting objects. Whatever it is in reinforcement learning, focusing on the objects that are more important and more likely for us as important features of image that we have. For example, here you can see that we have industrial arm, that it has a camera, that this is the working environment, so that reinforcement learning technique can directly, we will see how to directly feed the image into our algorithm that becomes deep one, but we don't like to interpret and use all the pixels independently. We want to extract features and use higher level features to train our algorithm and do proper action based on that vision that is coming to the environment. Is it clear? Any question? So here also another example. Let's say you develop this cute robot for yourself. Then you say, okay, let's this robot do something like this robot has owner, right? When interact with owner, at least look at his face and understand if he's laughing or interacting, so with rotation or something. So what can it do? It can extract it first from image that is seeing, your reinforcement learning technique, and detect the simple features, then detect higher level one, so that based on that can decide what should be the policy. And this policy should be talking, saying something based on the features that is detected. But the question is, we will see how to do that, no worries. But we have different layers of the detection. Like this is very low level, this is mid layer, this is higher level. Which one of these we should use as input of our reinforcement learning to detect the policy? So you think which one? Because we can use this layer, and that layer too, as input of reinforcement learning to extract the policy. Any idea? Yeah, say. I didn't understand. So, which one of these to use? This one?
It depends.
It depends. It actually depends on your problem that you have. What you want to do.
So what I was saying is you should choose the one which has the minimum size, but still can represent your problem.
higher value for your problem that you have. We would choose the one that represents your problem better, and it depends. That's why I'm saying it depends. So you may, your action, your policy maybe is just relates to the face, where the face is, where the human is. Then you give higher level, and you try to construct your network somehow. I will tell you, like more convolutions kind of to achieve this one. But maybe sometimes you also need to, like blinking, smiling or something, more feature of face you need it, then you may come here. Or even more features you come here. Different layers can give you more precisely, more precision on the data that you have. Based on the policy and what you want to do, then you can make it more accurate or less accurate. What is the advantage of using higher level features? Its advantage is like faster, because your state dimensionality is smaller, then finding policy for that is easier. But if you have more features, after your dimension is bigger, then your training should be more, your agent should try more effort to learn it, right? So this is the general idea and answer for which level to use as input. That as developer you decide to choose it. So let's say we have a picture of this cute cat, n times m. What we need to do in order to be able to use it with our deep neural network, first of all, we need to flatten this image to x of the n times m. It's kind of, you want to flatten it to array to give it as input all together. So it is in 2D, we just need to flatten it. Even in the code that you're writing, the image that comes, you write flatten it, open it as array, as input. After you open it, you give it here. Then lots of weights should be calculated with the SGD and the forward, feed forward and propagation steps. Then finally the output comes. Output, for example, here if you have classification, this can be cat, this can be dog, this can be bird, and etc. Then probability of which one it is, detecting which one it is. But the thing is that we don't use a special structure to import features only. That, let's see, what does it mean? It means that in deep learning techniques, we have very nice approaches to extract the features that we mentioned in the slides. So instead of interpreting the pictures and finding weights directly to the output, that is brutal and there are too many, very hard, we have a technique, very famous technique of deep learning that we can call it as constructing convolutional layers and sliding windows. It means that I kind of want to, if I have a picture or lots of information, extract important features of that and find weights instead of directly using all from start to end. Kind of, I want to reduce the dimensionality by extracting the features from low level to high level to understand what is happening and learning my weights. So the important technique is convolutional layer and sliding window. What does it mean? It means that you create a window like this blue one at the beginning. So this is your image. So this image is this image. You can like consider this is the image, and each one consider is the pixels. So just simple example. Then we create a window. Then after creating the window, we slide it on the picture. Slide it, and ends here. This orange one is slided after like 2 steps. Blue one go to the right 2 steps and moved, and come down and moved. And after doing that, if for output of whole this blue one is this one, just I will tell you how to do that. We will apply some filters to do that. So if the output of all of these, for example, these are numbers, right? If I sum up all of them, then write the number here. Then after doing that for all picture, I will have the new dimension, the new picture, like this one over here. The simplest form can be, if I want to make it understandable, a little bit here. So if I have this picture, so let's say this part is black somehow. And if I want to do something similar with some sliding window, where are the markers? Here. And kind of the motivation is like, this is too big. I want to make it smaller, but I want to have the information still. I can say, okay, this is my sliding window that I move like in bigger scales. Then if each one of these is something like same, then I will have a, let me draw it. I have a smaller picture that looks like this. And this one is this blue one. So the big picture comes to a small one. I have the same information that this corner is black, although I'm losing some information here. This is black, but still this looks like the same object, same frame there. Whatever I'm having there as picture, I'm still keeping it, but making it shorter, kind of getting average of that, average of that, average of that over here. The general concept looks like that with a sliding window. But how it's happening, that's a very simple form. This is like, of course, we have overlap that calculates the also whatever I want. And then we want to find how to find the weights of the neuron. So is there any question here? Is it clear, this part? The idea is I have a frame, lots of information. This part, I want to reduce it to just one neuron. This part, I want to reduce it to one. This part, reduce it to one, and kind of find the weights. How to do that? How the calculating the weights to achieve it? We can use different kinds of filters to weight the local features that I have, and based on the filter that I want to represent, I can define different filters. What does it mean? It means that, so I draw on some bigger scale shape, but of course I usually don't have like that. We have some object, like we have a table here that includes some lines. I kind of need to detect the features of this table, that is lines, are like lines here, line here. To detect that, I can use some filters, that this filter, for example, diagonal filter, represent this line here. So that applying this filter on the process that I have can represent the output that is useful as feature for me. Is kind of detecting this line in the image for me. This is diagonal. This is another way of diagonal. This is like detecting the multiply in the frame, in the image that I have. This is finding the sum. Is like I put -1 in other terms of matrix, and I put one in the way here. This is the edge. It means that if you have a picture of lion, if you apply the filter of edge on it, that is all -1. This one is over there, 8 and 1. Then you have that you detect the edge by applying this filter. Then we have the identity. That identity is exactly the same one. We have blurring. If you apply this filter on the image, 1/9 of 111, that your image becomes blur. If you apply the sharpen filter, this filter, with the convolution and sliding, if you apply it, you will sharpen your image. And rigid detection, if you apply this filter on it, just multiplying this matrix by the value that we have there, you will have output of this frame over there. So actually we are extracting features. If you look at here it detects the line, this one, and here we detect the edge. Here we detect the identity. This is just the same. Here we detect the blur. We make it blurring, sharpen, and the rigid. So, for example, if we have this picture as input, that is the word edge. if we want to apply filter sum, on this sliding window, for example, we move this sliding window, we are here. Let's see what is happening. This part of image is this part. And the filter that I have is detecting sum on the frame. So the product of these two will give me another matrix, then I can calculate the sum of this matrix that give me one value. And this value is actually the output of whole this area for me that represented as one value. And I'm doing kind of downsampling and extracting important features by the filter that I want to detect the, like this feature, the plus over there, to downsample my my picture and frame. Now the question is, can we do detection and downsampling and extracting important features just by one filter? Of course, no. We apply different filters. You may say, okay, how to know which kind of filter to use? So we can say, if you take a picture like this, everything includes edges, and edge is like edge, corner, plus, negative, or curve things. There are some general filters that if we use general filters, based on that general filters, we can make sure that all the features that we want are already existed. These are well known. You don't need to investigate again. You use general filters, well-known filters, but different types of filters, not only one. Different types of filters that extract, one of the filter extracts the edge, one of the filter extracts the plus, one of the filters extract the multiply from all the information that you have. So the features will be going to use to detect general. So this is low level, then we use this for general understanding of the information that we have in our image. Any question? Maybe a little bit confusing this part for who is new, but if we move, will be a little bit more clear. So in the left side, we have 5 times 5 image, whatever it is. You can consider it's a picture of lion or whatever. Just in a small dimension, we want to see what's happening. We apply 3 times 3 filter. The filter size can vary also. That this filter is like the same plus filter, like this is 1, and these ones are 0. So if we do that here, what we start from starting part with applying the same filter size. We multiply this region of the input image by the filter that we have. Then we get the output with multiplying this to that. It should be all 0 except this one. You see, multiply 0 by 0 is 0, 0 by 1, 0. So element-wise multiply, just this one is 1. Then the output is here 1. Then I apply the sum of all of these, 2. Then put it here, 2, new feature map. Then what we can do, if we consider stride 1, it means that I'm sliding the window with stride 1 step to the right. Can we change this stride? Yeah, we can move 2, move 3. But we should be careful that it's fitting with my input image size. So they start from here, stride 1, I slide 1 to the right, again apply my filter, then get the output, then get the sum, put it there. I'm explaining the convolutional layer and striding in the visual. Then we want to apply filter again, just one filter. Stride to the right again, apply the filter, get the output, just element-wise multiplication, then sum up, it becomes 2 value. Then here we move 1 to the downside and the left because its right is 1. Then multiply by the filter, then the output, then the sum of them is 4 over there by this example. Then we continue. stride to the right, then multiply, then result, then 5. Then we continue to the right again. Then we continue, then we continue, then we continue up to end. Then after doing this, what we have? The input image with the filter 3 by 3 and the new feature map that we have is output looking like this. The important information that I have, I'm keeping with extracting feature to downsampling that. Few questions are happening here. What should be the filter size? We can decide to how big it is. But basically 3 or 7 is enough even for big images. By experiment, we can have a look what others done for image processing application, what usually filter size is good, then we can choose it. What kind of filter already have done? There are a couple of filters that we can use the tools and apply on it on the layer that we have. So input image size, the filter size, then what is the important thing? Stride. And what is the step to move, slide on it? We decide on it as developer. If the step size is bigger, of course, then what is happening? The dimension grows quickly. The decreases quickly. But we may lose more data because then there is no overlap. If the stride is smaller, then I have more overlap, more confidentiality that I don't lose the data. That's the trade-off that we as developers should choose. Any question? So we say we have matrix or windows of weights actually here, that linear combination of them can be calculated, and it looks like this here, that all these filter goes there in the form of the convolutional layer, and all the things that I explained can be summarized in one line of code. How? We can write, for example, self that convolutional layer is equal to neural network dot convolutional 2D, input size 5 and 5, the kernel stride, the kernel size that is showing my filter size 3 by 3, then stride, the number of steps that I'm going 1, and we have a padding here that is 0. Padding is used when, look at here, like I have this size of filter, and I'm moving that stride 1, and I'm moving that with stride 1, and there is no problem, it continues here. But if the stride is 2, then what happens? Look, this goes 1, 2 here, 2 has no problem too here, luckily. Like kind of if you have 3, 1, 2, 3, then it goes out. You see? When it goes out, so I don't have anything here. To make it adaptable, you should calculate if your straight with the size of the window that you have goes out of your picture, then you can add something formal here that can be indicated as padding. You can make it bigger by add padding to make it okay that your sliding doesn't go out. Goes out actually, but there are some useless values that they're like 0, that doesn't change anything, and but it makes it okay for the calculations that you have. So all the things that I explained, one line, PyTorch. Okay, very simple. Just create a convolutional layer, get the input, kernel size, stride, and pattern. Now, if you want to see how it looks like on bigger scale, we have image, RGB. So we have one image. The size of it is X, Y, and Z is the RGB, 3 colors. If it's grayscale, we don't have those dimensions. Now what we do, based on number of filters that we have. So I'm applying filter number 1. And this filter number 1 is gonna be to apply the RGB independently, and number of filters that I have, I will have some outputs. What does it mean? For each one of these, although it is smaller with new size WH, based on this right and the filter size that I have, this is gonna be smaller. But since I have different kinds of filters and RGB, it's gonna increase. Number of layers that I have will be increased. The size gets smaller, the number of layers will be increased. But what is happening in short, that we have picture with some features and we have features here instead. Maybe if you look at the picture, you don't understand anymore here, but it has features that are more useful for image that I have. So kind of like extracting the important features here, because this is 0 here. This part will not be anything, 0 again. But this part, there are information that is passing to my downer layers. So by looking at this, you may say, okay, oh my God, the size is increasing. Instead of decreasing, we were trying to apply convolution, but instead of decreasing the size, it gets worse. Now we increase the size. What to do with that problem now? So to deal with that problem, we have another step that we call it as max pooling. The size is increasing. In some cases, not always, if we want to prevent that explosion of the size, we can apply max pooling. In max pooling, what we do, max pooling is very simple. The output that came from convolution, what we can do, let's say we have an image like this, and apply the filter, and we've got it. Now we can downsample it with some filters of max pooling that says, for example, take the filter like this, apply a filter like this, and take the maximum value. Simplest way. Apply a filter, get the maximum value. Apply the filter, get the maximum value. What is the maximum value? Is 5. Apply the filter, get the maximum value. Apply the filter, get the maximum value. So you may say we are losing lots of data. Of course we are losing lots of data, but we are decreasing the size and we still have the important parameters. For example, you see this picture here. The girl is visible. Applying max pooling, applying max pooling. The face is not visible, but still we can say there is human like there. But we are decreasing the size of the layer that we have. How we can do that in PyTorch? Very simple, one line. Self.pool local to, like this is like after pooling. Neural network max pooling to the kernel size, the size this size, and its rate. What is the size of the sliding? Here, the size will 3 for my example. From here, 1, 3, 3, 3. If you have 2, this will be a little bit bigger. Now, let's put all together. If we put all together, we have image. We apply convolutional with multiple filters. The layers will be increased. Then we apply max pooling. We decrease them. And finally, here we have the features that we wanted. Now we can apply fully connected normal neural network, fully connected layer, in order to calculate our output, whatever we want. In deep learning, up to here, we just did feature extraction. And feature extraction with lower dimension. And here, we just do the learning part. Classification, making decision, remembering, or whatever it is happening there is happening over there at the last stage. So, just some points that here we may need batch normalization. We studied already. So that output of the layers that we have to be normalized. How we can do batch normalization? We can write neural network, batch normalize the size. In this layer, the output will be normalized. One simple small layer. Just all the normalization will be applied here. And what is the nonlinearity that we set as activation function common here? We just mostly use ReLU. And that's it. It removes the negative value, and here we can have classification or prediction. Couple of points at the last stage. Or I already mentioned, so far you know, we have fully connected layer that we may use, like if we have classification, we may use softmax for output. That using softmax, the equation is looking like this. And in PyTorch, we can write neural network that softmax and the dimension that we have. That's it. So here you can see this is I implemented some specific applications. I changed the image because I didn't want to put it here. But this is what I implemented with some convolution. You can see applying convolution with kernel size 3 by 3. It means that what was the size of filter? It's right of 1, padding of 1. So I added also padding because of these calculations. Then it becomes like the input image was like 160 times 220. Usually you have big image, right? You don't need it. You just resize it to smaller, then apply the convolution. Convolution size will be also can be calculated by some equations, and you can write some codes to do that. If you go to interview for R&D of the deep learning, usually the question is calculate the size of, like after applying, they give you this input and they say what is the size over there. Then you need to calculate it. I'm giving you a trick for interview in future. So, here you have the image, then the size is increasing, the dip size is increasing, but it is compacting, making compact. Then I put it to fully connected networks. Then I was doing reinforcement learning, deep reinforcement learning with this technique, but this is part of some things that we will later see. So whole the scenario of deep learning can be discussed something similar to this in simplest form, but we have well-known techniques like YOLO. You look only once, that its network is looking like this. It is the image input. Then you can see a couple of different number of convolutional layers that finally goes like this, that does both of the localization and object detection, and finally output will looking like this, that this is dart, this is the chair, this is the bicycle, and that's the car, and by downsampling this. But of course, this has like details that I'm not going to explain for you. If you are interested in, go study it. We have different versions of YOLO, and you can see I put the performance over there. I think this is YOLO version 6, version 1, 2, 3, 4, 5, and we are in YOLO version 6 that outperforms all of the existing algorithms, is faster and much better to use. And if you are interested in, just see. Now it can detect 100. The base version can detect 100 different objects in one frame. You just give the picture as frame, and it says 100 different objects, where they are and what they are. That's keyboard, that's mouse, that's monitor, can give you all of those as output. We have different popular deep learning architectures. For example, LeNet, we have like Dan KrisNet, we have AlexNet, we have Overfit, we have BGG, and like GoogleNet, and many different bottomnet layer, and different kinds of networks that they are successful in different applications. For example, if you have a look at AlexNet, how does it look like? The image is coming, so you can see max pooling, different layers of max pooling, and different stride size. Instead of having one layer, they put 2 layers at the same time with different kinds of different characteristics, and finally fully connected dense layers and the output. So by looking at all these different networks, you see that most of the concepts we studied today, and there are different combinations, different structures that finally gives us a different level of the accuracy for prediction. This one solves the image classification problem with 1,000 different classes. Output is vector of 1,000 numbers, probabilities of the what is the output. For example, it is cat, dog, or whatever. You give the picture, then it tells you what is the probability of being cat, dog, bird, or whatever, and it can do it for 1,000. And you can download it and train it, or pre-train one with the weights. You can apply it on the ImageNet to see how accurate it is yourself. So popular deep learning techniques include convolutional neural networks. We talked about. We are caring about this for reinforcement learning mostly. We have another LSTMs, long short-term memory. I'm not going to explain. You can read it. We have recurrent neural networks, RNNs. We have generative adversarial networks, or GANs. We have radial-based function networks, RBFNs. We have the multi-layer perceptron, MLPs, and we have like self-organizing maps, or SOMs. That these are famous, but for reinforcement learning one, we mostly care on CNNs, and that we studied the most important things that we needed for our course. What does it mean? It means that we have robot. We can have a camera that sees whole robot, for example, or camera that is on the arm and sees the environment. NM, so we have state space. Based on this state space or observation that we have in our agent, we want to apply some convolutional layers to extract features. And based on that features that we extracted, after this one, we want to apply the algorithm of value function approximation to extract the policy in this part. The fully connected part should learn the policy from the features that it is seeing. So it kind of, the vision will be downsampled up to here, but at the end part, we want to put and merge reinforcement learning in order to learn the policy that we want to do. Instead of detecting this is cat, this is dog, say go to left, go to right, learning the policy. And there are different techniques. Some learn the value function, some learn Q value function, some learn directly the policy. And then the name of the algorithm on deep reinforcement learning will change. If we put all code together, you will have this code here. Class of deep learning. The initialization, initialize our network. You can look at, first of all, the super deep learning from the class of deep learning is not very important, is a child of the parent class that gets all characteristics inside to be used here. The important implementation that we have, so you need to put it there to get the features and child class that you have from parent of the neural network, make it simpler. What we do, we create convolutional layer 1 with convolutional 2D, the input image size, the kernel size, the stride, then padding. Then second layer of convolution, third layer of convolution should be, of course, the size of output and input matching together. Be careful about that. So here I did it with 3 convolutional layers. So you can add more, you can remove. Then after all of this, I added max pooling. Now you know what is it. Then here I've written a function that calculates the size of the the output size of the convolutional 2D. If you do convolutional 2D, I've written for you that like if you give the size, how will be the output. Then I created here the convolutional the W and H by calculating the output size by sending the parameters to that one that calculates it. Then here I have the size of final output, then the calculating the linear input size, the latest layer, fully connected layer, the W and H size times 32. That shows the output, how big it is after applying the convolutions. Then just creating linear function, the linear layer. 2 layers I added. Linear by the size that calculated here for first one, and second one should be the output of that one. And finally, we have the number of size of output that we want. In PyTorch, you don't need to implement backpropagation. No need. It is happening in background. In Keras, in TensorFlow, you need it, but here implicitly you need it. Here you don't need it. You just need to declare forward step. That in forward step you need to declare, for example, x1 as activation function. For first layer that we defined, we apply activation of the ReLU on the convolution 1, on the convolution 2 again ReLU, on convolution 3 ReLU, and return the function that we have after applying the forward passage. That backward is also happening here. So this is the whole construction of the network. And for training, of course, you need a simple loop to train and apply, for example, the SGD or whatever you want to train the network based on feeding the input to your network. Then that's it. Today we studied the perceptron, we studied the neural network, we saw optimization, backpropagation. We then talked about the adaptive learning, batching and batch sizes, regularization, and finally we saw convolution layers and deep learning concepts in minimum level that we need for reinforcement learning. Is there any question? This was the minimums that we need for deep reinforcement learning. No other way. We have to learn it, and you have to learn it to be able to do something there. No question? Okay, good. Thank you very much. For next week, think about your project, and you prepare your representation, and you need to come here, discuss it. And also, I may change it in class. I may change, no, that's too simple, or no, that's very hard, you cannot do. I will adjust it. For next week, everybody must report your project in the class. So thank you very much. See you next week. So Tony.